Hi, the title of our paper is WaveMixSR, Resource Efficient Neural Network for Image Super Resolution. I am Pranav and my co-authors are Srinidhi, Prathiba and Professor Amit Sethi. We are from the Department of Electrical Engineering, Indian Institute of Technology, Bombay. Single image super resolution aims to enhance the resolution of single images. This task has various applications in fields such as medical imaging, remote sensing and digital photography. Image super-resolution is a challenging task due to the lack of information to completely reconstruct the high-resolution output. In recent years, vision transformer and its variants have been outperforming CNNs in this task. Their success showed that long-range spatial token mixing by self-attention can aid in super-resolution. The application of transformers is limited by the quadratic complexity of self-attention with respect to the input sequence length, which can impose a large computational and memory burden on the GPUs. Moreover, transformers do not have an inductive bias, unlike CNNs. Therefore, they require a large number of training images to give good generalization performance. Recently, new token mixing models have emerged, which replaces self-attention in the transformers with other mechanisms such as Fourier transform, depth-based convolutions, pooling, or even spatial MLPs. These token mixers have been shown to perform on par with self-attention based transformer models without suffering the large data and GPU requirements. For instance, the WaveMix architecture, which uses two-dimensional discrete wavelet transforms for token mixing, has been shown to perform well on high-level vision tasks such as image classification and semantic segmentation while consuming low computational resources. We use WaveMix blocks introduced in WaveMix to create a new token mixing architecture for image super resolution. We propose WaveMixSR, a new network that employs spatial token mixing using 2D discrete wavelet transforms for single image super resolution. Our model is efficient in terms of computational resource utilization and parameter count. WaveMixSR consumes less than half the parameters and resources compared to other state-of-the-art models. WaveMixSR achieves state-of-the-art performance in multiple SR tasks on BSD100 dataset. It achieves this performance without needing a large training data and pre-training procedures employed by other models. Now let us discuss the architecture of WaveMixSR. The input image in the RGB color space is first converted to YCBCR color space. This conversion is done because YCBCR color space separates the image also into three channels, which is the luma and the chrominance. The Y channel, which represents the luminance information of the image, and the CBCR channels, which represents the chrominance information. Typically, in superposition techniques, only the Y channel is used for the path with parametric learning because only the Y channels contains most of the image details and is less affected by the color changes. Therefore, once we convert the image from RGB to YCBCR, we separate the channels with the CBCR channels going through path 1 and the Y channel going through path 2 as shown in the diagram. WaveMixSR initially upsamples the input image to the final image resolution using the upsampling process, which can be either bicubic or bilinear. The CBCR channels are directly upsampled to the final resolution and concatenated by the output from the path 2. In path 2, the Y channel goes and gets upsampled and then it is passed through a convolutional block to increase the channel dimension. Then it is fed to the WaveMix blocks. 4 WaveMix blocks are connected in series and then the output from the WaveMix block is transferred to another convolution block and the number of channels is reduced to 1. Now the output from both the paths are concatenated and the YCBCR output obtained is converted back to the RGB output. Finally, where we get the high resolution output image. The operations inside the WaveMix block is exactly as shown in this diagram. Inside the WaveMix block, the input first passes through a convolution layer which reduces the channel dimension by 4. It then passes through a level 1 2D discrete wavelet transform which generates 4 outputs. The 4 outputs are concatenated and sent to an MLP. The MLP has two linear layers with a nonlinearity in between. It is then passed through a transpose convolution layer to increase the resolution because the 2D wavelet transforms reduces the resolution of feature maps. After the transpose convolution, the output is passed through a batch now and then sent out. A residual connection is there within each of the WaveMix block. Now let us look at the results of WaveMixSR on various datasets. The graph shows the comparison of PSNR and SSIM for 2x super resolution on BSD100 dataset. It shows that WaveMixSR surpasses the previous state of the arts, HAT, SwinFR and HAT-L significantly by a large margin. We can see the table which compares WaveMix performance with other models and the training datasets used. We see that WaveMixSR achieves this performance gain without needing ImageNet pre-training like HAT-L and SwinFIR or training on much larger DF2K dataset. WaveMixSR just uses the smaller DIV2K training dataset and still manages to outperform all the other models. BSD100 dataset is a classical dataset composed of large variety of images ranging from natural images to object specific such as plants, people and scenery. Unlike other datasets like Set5 and Set14 which has very low number of images, BSD100 has reasonable number of images which gives a more accurate metric for model capability on common images. Urban 100 too has larger number of images, but it only has urban settings with buildings which mostly have a periodic lattice structure with windows and straight lines. BSD100 images have more variation in shape since it contains large variety of images, and the performance of WaveMixSR on BSD100 datasets demonstrates the ability of our model to generate high quality natural images. The computational and parametric complexity of our method was compared with the other state-of-the-art transformer-based models such as SwinIR and HAT as shown in the table. We see that WaveMixSR is highly parameter efficient compared to other models due to the presence of parameter-free token mixing using 2D discrete wavelet transform. The self-attention, channel attention, and cross-attention in transformer-based methods introduce 20 to 10 times more parameters compared to WaveMixSR. WaveMixSR also saves on computing as it uses half of the multi-add operations compared to SwinIR and one-fourth that of HAT. Now let us look at the qualitative results. The first column shows the patch of the original image, the second column shows the low resolution image, and the third column shows the model output. We can see that our model was able to generate the star emblem and sharpen the image. It also shows the ability of our model to regenerate the facial features which were blurry, and it was also sharpened. It could also reconstruct the lines in the faces and the eyebrows properly from the low resolution. In this image, we can see that the blurry person has been completely reconstructed. In this image patch, we can see that the stripes in the bird was also perfectly reconstructed. It could also clearly reconstruct the windows in this particular diagram. In this paper, we propose WaveMixSR, a wavelet-based token mixing model for image super resolution. Our model uses 2D discrete wavelet transforms as a token mixing operation for high resolution image reconstruction. Experiments shows that WaveMixSR performs well with natural images and achieves state-of-the-art results in BSD100 dataset. It consumes only a fraction of the computational resources and is highly parameter efficient compared to the other SOTA models. Our model was also able to outperform other models without resorting to the pre-training on large datasets or adversarial training. Our work shows that token mixers can be employed in low-level vision tasks such as image reconstruction and can perform better than transformer-based models using much less resources. Thank you all for listening about our model.